Well, let's officially start. I'll share a first slide and then pass the word for the beginning to Javier.
Thank you, Silvia. Just because we are running out of time, I think I just wanted to say hello, everybody, welcome to this meeting. Let me start by saying thank you to the organization. It's been really nice to have the opportunity to have this meeting for Jpas. Thank you, Benjamin, Cheska, and everybody involved in the organization of this meeting. Also to remind that this meeting is open. It is not restricted to the members of the collaboration. This is open to everyone who wants to join. And the goal of the meeting is essentially to present and to inform the community about the progress, about the new achievements of Jpas in the last couple of years or so. And that's it. Just to say thank you again to the organization, welcome to everybody. And because we don't have much time, I would like let's start, Silvia, and we will move on with the schedule.
Okay, so thanks also from me and and all of us of Jpas for having this session. This is the program. I guess you've all seen it and most of you received it. The first hour or so, we'll try to keep it shorter, will be dedicated to general presentation, both of the Jpas project. We'll have a brief overview of the first light of JPCam. Many of you must have seen the news that went around today on the first light of JPCam, which is a great milestone for us. Then we'll talk about mini Jpas, which is a little tiny compared to Jpas survey that we carried out with an interim camera. And we have some first data then with all the Jpas filter and some first scientific results. So we'll briefly present that project too. We will not go much into details in the first hour, but just have general overviews, and then there will be a break. We'll have to be tight on schedule for that because at from 5:30 to 5:45, there is the closing remarks of the SEA meeting. Then we'll resume at 5:45. For a last hour of actually discussion on the science. All the working groups of Jpas will present themselves and also give an update on the science that they're already doing with the mini Jpas data, and also forecast and plans for the upcoming Jpas. All right, so very quickly, for those of you who don't know what Jpas is or what are the specifications of Jpas, so Jpas is a wide, we plan to observe about 8,000 square degrees of the northern sky. It's a wide multi-band photometric survey. So its characteristic are really the 56 filters that we're gonna see in a couple of minutes. It's primarily a Spanish and Brazilian collaboration. The collaboration board as representative from the 4 founding institutions, CEFCA, the IAA on the Spanish side, and Sao Paulo, University of Sao Paulo, and Observatorio Nacional on the Brazilian side. It will be carried out from this new observatory, the Observatorio Astrofísico de Javalambre in the Sierra de Javalambre, close to Teruel. It's a relatively new observatory with extremely excellent, with very good sky conditions for being in continental Spain. It is composed primarily by two telescopes. The primary one, the Javalambre Survey Telescope, is a 2.5 meter, and the auxiliary telescope is an 80 centimeter telescope. They're both characterized for having a very large field of view. So the goal of this observatory is really to carry out large photometric surveys. And the observatory is an ECTS, so it's a singular technical facility of Spain since 2014, which means that 20% of the open time, of the observing time is open for competitive calls. So the small telescope is devoted to the J+ survey, and we're going to hear about it in a minute, while the large telescope, the 2.5 meter telescope, will be devoted to Jpas and also to the observation of the G band for the Euclid survey. So this is just just to give an idea of the field of view, why these are like survey telescopes. This is compared to the moon, the size of the main instruments of the two telescopes. On the left is JPCAM, the instrument that had the first light, that was announced the first light today. It's composed of 14 CCD. Each CCD is larger than as a field of view, larger than a full moon, so more than half arc minute on the side. While the TATCAM, the main instrument of the 80 centimeter telescope, has a field of view of 2 square degrees, if I'm not saying anything wrong. And actually we hear a few words on Jpas because, you know, it's let's say the sister of Jpas, so we want to mention a few words on it. Carlinhos will continue with the next few slides.
Yeah, can you hear me?
Carlos, yeah.
Okay, thanks Silvia. Yeah, just a few words about Jpas, the Hablumbre Photometric Local Universe Survey. Jpas is being conducted with the small telescope. At the end, in addition to the large field of view that we have, 2 square degrees, the unique capability of this survey is the filter set is only 12 filters. In this case, basically the usual SLOAM plus 7 medium or narrow bands that are located in key features of the stellar spectra. We will hear about that later. Jpas is gathering information since 4 years ago. The first data release was made public 2 years ago in Salamanca. That was 1,000 square degree, basically. With these 12 filters, you can access the data. They are public in the link that you have there. And we expect the release, the second data release with more than 2,000 square degrees in October. The initial plan was to make it this release in the SEA, but okay, you know the situation. So in the next slide, you can see some of the highlights that Jpas already, some studies. This large area that we cover and the custom medium bands, that some of them are unique, provide very nice science with the sparse of emission line objects. For example, looking for halo planetary nebulae that are very, very sparse or very strange energetic Lyman alpha emitters at a redshift higher than 2. And also, because of the field of view, we can perform if-like studies in the nearby universe, like the study of San Roman et al. 2019. So this is basically the summary, just you to know. You can go to the webpage and learn more about Jpas.
Okay, thanks, Carlos. So so we move back to the main telescope, the main instrument, JPCAM. It's a 1.2 gigapixel. I just skip this because, you know, we will hear at the end of this next first short presentation, we'll hear about it from Tony directly. And this is an image of the JPCAM team with the JPCAM installed. So Jpas, as we were saying before, its unique feature are the filters, a 54 narrow band covering the entire optical spectrum, complemented by 2 broader filters in the blue and red wings. So this is effectively will deliver a pseudo spectrum for every object or every pixel actually observed in the sky that Jpas will observe. What does this mean? So that you can characterize not only that you can characterize objects very well, you have you know, you can almost have the SCD, the full SCD of objects. And for extragalactic studies, this means a very accurate photo Z for the sources, for all the sources. This is the current planned footprint of Jpas. So the red one here, I think you see my cursor, is the Sloan footprint. The blue is the expected footprint for Jpas. We expect to cover approximately 700 square degree per year, but this is still pending, and the general survey strategy is actually under revision and will be finalized soon. So the OJ observatory is run by CEFCA, and CEFCA is also doing a great job in all the data processing and storage. The UPAD, the unit that is working on the processing of the data, the UPAD team, and data collecting and processing is also based at CEFCA in Teruel. So a very, very quick overview of Jpas science. What are the main goals of Jpas? Although I will really go through this very quickly, because in the second hour, we will really hear about that in details from the groups, for all the science working groups of the collaboration. So for its nature, Jpas is really versatile, because you will have a good characterization of all objects you're observing. You're not you don't suffer from pre-selection of sources like in spectroscopic survey. You don't have problems like fiber collisions. Of course, you have less redshift precision than spectroscopic survey. One of the main targets of Jpas is actually to carry out cosmological experiments, in particular the study of the large-scale structure, the clustering of BAO, baryonic acoustic oscillation studies for galaxies between redshift 0 and 1. So as we will hear later, we expect to do a very good mapping of the large-scale structure in the universe up to redshift 0.5, 0.6, and as slightly higher redshift to do a very interesting and competitive clustering analysis. And at higher redshift, at redshift above 2, we will actually use quasars and Lyman alpha emitters, for which we will get also extremely good photometric redshift to do also clustering analysis, both by ourselves, let's say Jpas only, but also in collaboration with other surveys. In the case I'm mentioning here, in the case of quasars, the plan of the WEAP QSO survey is actually to follow up alpha million quasars from Jpas, not only to study their clustering, but also do studies of the IgM and the Lyman alpha forest of these high redshift quasars. Clusters also, it's a very interesting, other interesting topic for Jpas. Because of the very accurate photometric redshift accuracy, we can actually assign, we can find clusters down to relatively low masses, down to group masses of few times 10 to the 13. And this, when combined with also lensing analysis, so we will take broadband observations in the best nights of in the best photometric nights. And so when combining also lensing and cluster, this will be a quite powerful, Jpas will provide very powerful data also for cosmological studies with this combined set. And in this, let me also mention the collaboration. We have an MOU with the German Rosita, with which we overlap of about, we have an overlap of about 2,000 square degrees, and also, combining X-ray, lensing, and optical richness would be very important for mass calibrations for cosmological studies with cluster. Galaxy evolution, having very large, extremely large samples of galaxy of all types, obviously will provide also very interesting data sets for analysis of the galaxy formation and evolution up to redshift 1. And also we'll hear some first results on these with the mini Jpas data. For very nearby galaxies also, a few type of studies can be done. Which effectively means like you can, divide and cut your galaxy in little sub pieces and understand the stellar population properties of the different parts of the galaxies. Yeah, this is a nice illustration done by Carlos on actually what this actually means. So it's 2D science, so really looking at galaxies and how they evolved in 2D, not in 2D, and in their extension can be done up to redshift 0.1 with Jpas. And PDF science, so it means like integrated the general properties of galaxies. We expect for normal, let's say, galaxies to be able to do it up to redshift 1, and then for special galaxies like Lyman alpha emitter or quasars to extend it up to redshift 4 or 5. But also galactic science, coming back close to our Milky Way, also with this SED analysis of the, let's say, using our photospectra, which we started calling J spectra, this low resolution spectra that Jpas can deliver, we can also understand the properties of stars in quite details. And some of the most promising things are also looking for streams or more dwarfs in the northern hemisphere, so go deeper than what Sloan managed to do in the northern hemisphere in terms of finding dwarf galaxies. Also, it's interesting, just to mention some topics, the metal poor stars, who search for extremely metal poor stars, which are very rare. So really wide surveys are what is needed for this kind of studies. And again, we'll hear more about that later. Okay, so what's the current status of Jpas? We heard that the JPCAM just had first light, and we hear more details now in a minute. And we expect to start the Jpas survey at the end of this year. To keep ourselves busy with an interim camera, what we call Jpas Pathfinder, we did this small survey called Mini Jpas, and we'll talk about that and the first data and the first science result just after Tony talks about the first light. So I actually stopped sharing. Yeah, maybe we hear Tony, and then if there are a couple of questions on this first part, and then you can also add the questions in the chat, and we'll try to answer them.
Okay, I guess you can hear me and see my presentation now?
Yes.
Okay, so this is just a hot news from today. So as you know, today we released the press release showing or letting the community know that Jpas has successfully gone through the first, the technical first light. So I want to very briefly show some of the preliminary results that we obtained during this technical first light. Before that, and just for warming up purposes, this is a slide showing JPCAM in a nutshell. So I won't go into any detail because most of you are aware of and know the instrument. If some of you want additional information, I will be happy to answer or to send additional information over the email. So JPCAM is a panoramic camera installed in the JST T250 telescope. It's a 2.5 meter telescope. Large field of view, 3-degree diameter is shown with this blue circle in the slide. It has a physical size of about 476 millimeters, so it's a very large field of view. And JPCAM is the panoramic instrument, the Havalambre panoramic camera that has been conceived, designed, and manufactured specifically to exploit the survey properties of the telescope. So it is a large field of view mosaic camera. The scientific mosaic consists of 14 large format CCDs with a total of 1.2 gigapixel camera. That makes, just in the number of pixels, that makes JPCAM the second largest camera, astronomical camera. And it is equipped with a mechanical unit, the filter and shutter unit, able or designed to admit the Jpas filter system that you can see in the upper left figure here. So the combination of large field of view, 2.5 meter telescope, the high resolution of both instrument and camera, and the filter system makes this telescope plus camera system a very powerful survey tool, a very powerful system to perform astronomical photometric surveys. So this is a few pictures. The upper row shows the latest stage of the JPCAM AIV process. The left, you can see the JPCAM, the cryogenic camera, which is the most complex subsystem. It contains the CCD mosaic that you can see there. Ian Palmer, Teledyne E2B engineer, is there just for scaling the size of the instrument, And then the other three pictures in the upper row show the integration of the JPCAM at the observatory clean room. Once the camera was integrated in the clean room, it was transported. You see a picture down left in the slide, transported from the clean room to the telescope. It was, as you see, the room was just enough to transport this massive instrument. And at the end, we approached the instrument at the telescope. That happened sometime late February, early March this year. Then the COVID impacted, the whole world and the observatory in particular. So we needed to slow down the integration, but continue working until in June 2020, the camera integration was completed at the telescope. So you can see there a couple of pictures of JPCam integrated at the T250. It's a 1.6 ton instrument. Then we started the first light in June 29, a couple of weeks ago, and I'm showing here the first focused image that was already taken with JPCam at the telescope. So you can see that this is raw data. In fact, you can see in the image very clearly all the 16 amplifiers that every detector has. So you can see as black lines the pre-scan and overscans rows and columns. And then we pointed, in this case, to the North America nebula and took a 30-second exposure image using the Sloan J filter. I have to say that the telescope and camera performances were not maximum, in particular for different reasons. The alignment of the system or the focusing of the system was performed only at the focal plane level. So for those of you that you are not aware, the telescope has an active control on M2. M2 is held by an hexapod that allows us for very precise movements in the 5 degrees of freedom. And also the focal plane, the cryogenic camera, is supported by the actuator system. So we have at the end, in order to align and to focus the system, we have 10 degrees of freedom. In this case, for that image, the image quality control was not applied to M2. So we focused the image only using the actuator system, JPCam actuator system. We focused the image only by moving and tilting the focal plane. That means that some spherical aberration is expected in that image for that reason. Also worth mentioning that there was no auto-guiding working at that time. And the conditions at the observatory at the time we took that image, we had the scene that was oscillating between 0.6 and 0.75 arc seconds. Then we took that image, we proceed with the analysis of the image quality of that image. In particular, more than 28,000 stars were taken into account. And this is the PSF distribution that we observed all over the field of view. So you can see that the PSF was 0.88 arc second with a homogeneity of about 10% over the whole field of view. And you can see that in the image. So you see probably in the lower left side of the image that there is like an increase of the full width hub maximum, but it is our opinion because we are observing the nebula, the North American nebula, the number of useful stars in this region is much smaller. So we think that this is not really a degradation of the image quality, but this is the result of the adjustment of the surface. So that was, for us, this is great news because with this test, it is demonstrated that the image quality of the telescope plus instrument is so far within specs. We are obtaining a 0.88 arc seconds image with the telescope running in a and camera running in a degraded mode. So we expect to improve those numbers once the commissioning is progressing. But these preliminary results are very, very promising and very good. We were delighted to see how the image quality was at that level and with that level of uniformity in the first image that we focused. And then I'm showing here another example of the image that we took during the technical first light. This is for the press, is M31. This image is a longer exposure, 300 seconds with the same filter, Sloan J filter. In this case, we didn't use M2, but we also didn't use the actuator system to focus the image. So we can see that there is some degradation here, some gradient in the PSF, but that was expected because that image, none of the image quality control loops were applied. And this is a very basic reduction of the image using just bias and flat fielding reduction. But I think it speaks by itself. And that's it. Just wanted to highlight this recent news and to share with the whole collaboration and the people interested the results, the first results of JPCam on Sky. Thank you.
Thank you very much, Tony. Is there any question so far? I think you should be able to speak if you want. Otherwise, just write on the chat and we'll try to keep track and maybe reply later. Okay, so let me share and move, given that we are late ourselves now. So let's move to mini Jpas. So real data that we have in hand. So as I said, so before JPCam that we just heard about was installed on the camera, the 250 survey telescope was equipped with an interim camera that was used to perform the last technical check of the telescope and also for scientific operation. So with this camera is effectively one CCD of the final JPCam with the same resolution and a field of view of approximately 0.3 square degree. So we carried out several observations. In the main ones, the ones that we really, so far we have used the most, and we used as a sort of test survey, are 4 pointings along the extended growth strip on the what is called also Aegis field. And we dubbed these observations mini Jpas. So we observed it with all the 56 Jpas filter plus U, G, R, and I. And this also, I want to thank also the OAJ operators, but also for the great work in observations, but also the technical team that was changing the filters on the filter wheel of Pathfinder very efficiently. Okay, so this is actually how the extended growth strip looks through Pathfinder eyes with some zoom in some nice areas where you can actually see nice big nearby extended galaxies. These are the depths that we reached. So the telescope was needed recoating before when we took this with those observations, was a bit dirty. The main mirror. So we had to expand the exposure times. Now the mirror before the installation of JPCam has been successfly recoated, and the reflectivity is very good. These are so in this 1 square degree approximately 0.9 square degree after masking along the extended growth strip. We have 65,000 objects selected in the R band, plus 600,000 objects selected in individual bands. So here there are very interesting kinds of studies that one could do, for example, search for extreme emitters. So objects that only emit in one band. So these are the depth. In the graph, you find the depth. So the dashed line on the left indicates the approximate minimum depth that we want to reach with Jpas. And then with all the colors are the average depth of the narrowband filter on the right of the broadbands that were observed. So we're always between 22, 22.5 and 23.5. With Jpas, the exposure times will be planned such that we'll have more homogeneity of the depth in the different narrowband. Image quality, so all the observations of the narrow bands are always below 2 arcseconds, with the broadband being observed, in particularly the R band, observed in the best nights, and with the averaged full width of maximum of the images as about 0.7 arsecond. And here also thanks for UPAD for processing beautifully this data and delivering a wonderful data set for first analysis. These are just a couple of images on the data processing. Here you see before and after how an image is when you take it from the telescope, and after the processing from the UPad, how it looks after. On the right is the error in the astrometry, which is below. It's a few percent of the pixel size, 0.03 arcseconds. And then a few details about the calibration, and this I pass again the microphone to Carlos.
Yeah, thank you, Silvia. Can you hear me?
Yeah.
Perfect. So as you can imagine, the calibration of all these narrowband, some of them are looking to the sky for the first time with mini Jpas, so there is no, in principle, no reference for them. So as you here you can see an image that I stole from Jesus Varela's office, in which you can see what is the original plan for calibrate the Jpas images. So the idea is to start from J+. We obtain the set of the sources in the image. We make some spectral fitting to derive the best stellar model. This is the reason of the filter system of J+. So this is now you can understand why we have these narrow bands in key stellar features. Now that you have a stellar model, you convolve with the Jpas filter system, and you have your reference stars Jpas. So this was the idea. This was the initial plan. In this 4 or 5 years of J+ operation, we faced several challenges also to calibrate J+, so was not easy at all. So in the next slide, I provide what was the final calibration for this mini Jpas with all the things that we learned with J+, basically, that are in the paper published the last year. We arrived to these steps that you can read here. Basically, we use Gaia and the best sources in the image to derive a set of main sequence calibration stars. Then we anchor the photometry to pan stars in the broadbands, G, R, and I. And because we have G, R, and I photometry already calibrated, now we can create color diagrams with these 3 bands and a narrow band for which we don't know the 0 point. But in this color diagram, this is the only free parameter is the 0 point of the narrow band. So with the stellar locus, we can homogenize the photometry in the 4 pointings, and then we anchor the absolute calibration to 40 Bose spectra that are in the field. There are stellar spectra that covers most of the wavelengths that we are looking at, except from UJava and UJPAS that are calibrated and are anchored to the J+ photometry directly. So, but several comparisons that are not very extensive because the statistics is low right now, we estimate a conservative 4% precision in the photometric calibration. So that means that we expect 4 or less, or if there is something weird at this level, can be due to calibration. If it's higher, probably it's because of different issue. So the thing is that with J+ and everything in the next slide, we can see the prospect for Jpas. We learned that the initial idea was not good enough to cover the specification. So what we are going to do with JPCam at the end is to observe with large dithering. At the end, Jpas has 4 exposures. So each exposure is going to be taken with a large dithering of half CCD and in compact areas. With that, we ensure that we can homogenize or data in the narrow bands and in the broad bands without need of external information. So we don't need other surveys to calibrate, to homogenize, and then we are going to make the absolute calibration in the colors just for using the white dwarf locus. So because we are going to have a large area, we can use the white dwarfs that are sparse, but we are going to have several hundreds. We know very well from models what are the expected locus, so we can basically anchor the colors with the white dwarf that we observe and the models that are well understood. So basically, with a few exceptions, we don't need, or we hope not to need, any external data, basically, except for probably the reference band to calibrate the colors in Jpas. So we expect like 1–2% precision after the first 100 of square degrees of gather. At the end, J+ was defined to ensure the Jpas calibration, and that was the case, but not as we expect at the beginning. So in the next slide, this is about calibration. So now continuing with the quality and the features of the data. Here you can see the completeness of that we obtain. This is a work from Luis Diaz Garcia that was comparing the mini Jpas data with the deeper hypersuprime cam information in the field. Here in red is the completeness as a function of magnitude for galaxies, and in green for stars. And you can see some points and shaded areas. This is the comparison made by Luis. And then we have the solid lines that are the recovery rate that we obtain from fake sources that we inject in the images. This is very important because we don't have HSC in all the Jpas area, neither in the narrowband. So if we want to have some completeness in all the area and in all the filters, we need something based on the injection of fake sources. And this provides that we can do this job and have a fair representation of the completeness with these fake sources. In the case of mini Jpas, basically we have limiting magnitude at 95% of 23.6 for point like and 22.7 for extended. So in the next slide, we also provide in the catalogs 2 star galaxy separations or classifications of the sources, one based in a Bayesian modeling, and then 2 based on machine learning techniques. So at the end, by combining the morphology and the colors, we are able to provide a very good classification of the sources in stars and galaxies. And in the next slide, we can see what happened when we combine this star galaxy classification with the completeness in the find end and with the area that we provide, this masked area, because we also provide mask of bright stars, low signal to noise areas or low exposure areas and artifacts. And when you combine everything, you should obtain the proper number counts bound for galaxies in green, that as you can see falls perfectly with the expectation from deeper or previous surveys, and also for point like for stars and quasars in this case, that follows the expectation from the trilegal counts that we expect at this location of the Milky Way, with the IG's field is. So these are basically tests to demonstrate that everything is under control, but the unique things of the unique information of Jpas, mini Jpas, is in the colors, as Silvia is going to show us.
Yes, so we move actually to how our J spectra look like. So real images and real J spectra. So just a few examples, this nice plot made by Vinicius Placco. So you see here the insets are actually in this case are stellar objects for the specific snapshot, and the colored are our points, our photometric points, and the gray is the Sloan spectra. You can see how moving from blue to red star, also not only the general color, but also the unique feature of stars can start being are visible in the photospectra of from our data. And other examples here, galaxies and quasar. The first 4 are galaxies. This is an emission line galaxy. You can see the H-alpha emission. Red galaxy with a strong 4,000 angstrom break, another emission galaxy at a slightly higher redshift, another LRG at also slightly higher redshift, and then moving really to the higher redshift range. Here it's a quasar at redshift 1.7, and here one at redshift 4.2. And you see how the nice broad emission lines can be clearly selected from the data. Which, all these features really mean that we can derive very accurate photometric redshifts. This is a snapshot. I think in the galaxy evolution part, when we discuss later, they will also show this, just to show also how a nearby galaxy look in the different narrowband filters. So the photometric ratio, which is one of the key point of Jpas, this is a work by Antonio Hernán Caballero, using a personalized, let's say, version of LEFAR, a template fitting code. He has derived the photometric redshift that are available so far from the for the mini Jpas. There will be more derivation of the photo-Z from other groups in the future as well. What here achieved so far is a very good performance. It really meets our expectation. So we reach 1% of better precision for the photometric redshift for all sources up to 22.5 in the R-band, and 0.3% precision, which is what has been defined as the target for cosmological clustering experiment for half of the sample. So you can see here the sigma and MAD, which is used as a proxy for the precision of their photometric redshift solution, versus magnitude for different completeness. So for different cuts in the goodness, let's say, of the sample, 100% is the whole sample, and 20% is the 20% sample with the best photometric redshift solution, where even up to 23, you get below 0.3% precision. And on the right, you can see how it changes for quiescent and star-forming galaxy. Generally quiescent galaxy, because of the 4,000 angstrom break, their redshift precision is better down to fainter magnitudes. So from photo-Z to cosmology, really just a couple of slides, and then we'll hear more later. This is a nice image showing the DEEP2 spectroscopic. So on this field, there are there is a DEEP2 spectroscopic survey, and the blue ones are the points from from the spectroscopic redshift, and overplot in yellow are our photo-Zs, and you see how really the large scale structure, it's well defined with our data, with the photometric redshifts up to relatively high redshift, up to redshift 0.7, 0.8. Of course, that debates not, there are objects that there are wrong photometric redshift assigned, but the overall tracing of the large scale structure is quite nice. And also here an image of the most massive cluster that was detected in the field. Also in yellow, these are the redshift. In yellow are the only two objects known with spectroscopic redshift, and in white are the redshift or all other members of this cluster, which were unknown before, which we could assign to the cluster thanks to their photo-Z. Okay, so this is just to mention, this is really the beginning. Mini Jpas is already giving us a lot of data to play with, but Jpas will actually be 3 orders of magnitude more in terms of area, amount of data, and volume, obviously cosmological volume that we can probe. So we'll hear more about first scientific result in more detail after the break. So looking at the time now, we were supposed to finish a few minutes ago. In 8 minutes, I think there is the closing remark of the SEA. So we should aim at having the break at now I pass the word to Alessandro, who will briefly mention how to look for the data. While I speak, I stop sharing. How to navigate in the data portal of Mini Jpas. Alessandro, I think you need to be even more concise than what we originally planned, because at 4:30 we should really break for 15 minutes, and then we'll resume. So if anyone wants to listen to the closing remark, of course they have the time to connect there. And then after 15 minutes at 6 in Spanish time, we reconnect. We come back here again. We'll probably leave this open. So if you want to stay, you just stay. And then we'll come back for listening to the details of the science. Ale, to you, and in 5 minutes I'll shout.
Yeah, just make me a sign. Can you hear me?
Yes.
Loud and clear. Cool. All right. So we have all this data. What are they? You may be wondering. So you go to archive.cifca.es catalogs. What I'm going to show is the result of a series of requests that came from the Jpas collaboration And it's a whole work that many years ago started with a health interaction with the Spanish Virtual Observatory. And of course, I wouldn't be able to give this talk if it wasn't because of the people of the Unidad de Procesamiento Archivo de Datos in Teruel. And at least I would like to emphasize a couple of people, David Cristobal, who's the former head of the UPAD, and Jesus Varela, who's here, I believe, and the current head of the UPAD, and the brilliant work of Tamara Sivera and Javier Hernandez. So once you go to the archive webpage, this is what you get. And mini Jpas is down here on the left. And of course, the PDF doesn't work. This is what you get when you connect to the catalog portal. Make sure you click on that link. Please go on another one. And right, so on that link, there is all the information that you need to know about the data release. Please read it before you start playing with the data. Don't go to play with the data right away. Silvia, please go on. And read the manual. So the data are in this other link. Please, Silvia, click. And this is what it looks like. Please, Silvia, click again. Yeah, it was supposed to be a little bit faster.
Yeah.
So if you're not registered yet, please do so here. But if you're registered already, or if you've done it, you just click on that link and you just start playing with the data. Go ahead, Silvia. Silvia, please go. All right, so we have a series of services that we're offering. And I'm not going to go through all of them, of course. I'm going to show only a couple of very good examples. Please, Silvia, go ahead. Silvia, please. Right, and click again.
I'm on the Sky Navigator. I think it's a bit slow in loading.
Oh, okay. Oh, yes, sorry. All right, so the first example I want to show you is the Sky Navigator. Please, Silvia, click again. You can see how to filter the data. Please, Silvia, click again. And you can see that blue objects are stars, red objects are classified as galaxies. Please, Silvia, click again. Yeah, it takes a little. And you can filter your objects with search your objects by name, or you can search your object by coordinates. Please, Silvia, click again. And I'm not going to enter too much into this. Once you click on an object, you get very much the ID card of the object. You can see, please, Silvia, click again. You can see the spectral energy distribution, a preview, or you just click on Explore Object and you just go to see the full information that we have about this object. And the information is vast, and here you can get all the photometry information. You can get spectral energy distribution. You can get the cutouts of the individual object that you care for. Please, Silvia, go on.
It's the consearch.
Right. So, and yeah, keep going. We have a consearch, which is possibly the most basic search you can possibly do. Again, you can search by object name, by coordinates. The search is quite, can be arbitrarily interesting, and it gives you a list of targets. You can click on Explore Object and it goes again to the same Explore Object window as before. But Silvia, please, the most powerful way is the bioasynchronous queries. Please, again. This is a beautiful tool. Please, Silvia, click again. But what do I do if I don't know about asynchronous queries? Well, there's a beautiful help that you can go there, check it. It gives a very interesting, very good preview of SQL. And on your left there, there's the description of all the tables with all the fields that you that you want to search. So all the information is there. And then you get this information, you go back to the query, you make a query, you can make a very easy query, you run it, and you get the result. This is where you run it, then you can actually, in some cases, you can do the preview of the result. And then you can do more sophisticated queries. These are the query. This is an example of a query that students of mine have to do here with me. Maybe I'm not too kind to them. And basically in 5 minutes, you may manage to get a color manner diagram of all the stars in mini Jpas, the ones which have a, just by chance, when I did this color manner diagram, the left-right object is the same white dwarf that had been showing at the beginning. Of course, since everything of this is within the virtual observatory, you can do this within TopCat, within Aladdin, and all your usual VO tools. So you can get all the images, all the catalogs, and all the masks. They are there for you. So, you know, mini Jpas data have been waiting for you since December. Go there and enjoy, and thank you very much. Sorry for the
Thanks, Ale. Thanks. Very well. We are right on time. So, okay. So I'll stop sharing here. If any of you wants to go to the final remarks, I hope they're not in the same Zoom link. I don't think so. So at least we have a different room for us. You know, a few. Maybe some of us, you know, can stay here, and if you have any question in the meantime, we can answer them. I see there were some questions on the side. Carlos, you were replying to some of them. Do you wanna? I think he's maybe gone to the.
No, I'm around. I think I addressed all the questions. Maybe you should ask people to ask questions in case they still have some.
Yeah. So please feel free to unmute the microphone. I don't know if there is anything, Carlos, that you want to report. Any question that you think might be worth mentioning louder?
We got any question? Where can I check the data release scenarios? Maybe Ale can address this question better than anyone, or Jesus. I guess Borja is asking on the different data releases, which are presumably all of them in the same catalog web portal from the OAJ, from CEFCA.
Yeah, so you can find different data releases of JPlus. And Jpas, as of now, there is only the one public data release, the one of mini Jpas that was just presented. Borja, in case you meant something else, just you can unmute or write, or maybe Borja is, I think, oh, you're unmuting, I see you.
Yeah, thank you, Silvia. Yeah, I mean, it's an ongoing survey, so I just asking what is the scenario for the future releases, if you have a plan.
Right. So mini Jpas is well, mini Jpas as it is not ongoing. It's finished. So this current data release will be. I'm not sure. We'll do a new data release with mini Jpas. Maybe Jesus could then reply on this. We haven't discussed that actually. For Jpas, there will be different data releases at different phases of the survey. And different data releases might have different processing, different, slightly different procedures. So, you know, there is documentation attached to any data release. And, you know, the data releases of Jpas will just keep growing in size as the survey will grow. Jesus, do you want to comment on that as well?
Okay, sorry. Well, regarding, can you hear me?
Yeah.
Okay. Regarding mini Jpas data, right now we are not considering to do an additional data release because right now we have to focus on the processing of JPCam, and JPCam is already producing data, actual data. So I mean, it's not going to be straightforward. In particular, the first months. It's true that thanks to mini Jpas data, we are going to, I mean, we are already prepared to some, at that time, surprises that we got when observing with the 56 filters. And then right now we are, I mean, we expect to have less problems with JPCam than with mini Jpas data. But in any case, it's new data, it's new instrument. We have no idea which are the surprises, so we can, right now we cannot, we don't have people power to do a data and another data release with mini Jpas data. Regarding the data releases of Jpas, I cannot say it because this is something that has to be decided at the level of the whole collaboration. So, I mean, from the technical point of view, I guess that it would take still months until we have data to do scientific exploitation. In particular, for how it's observing with the camera, the actual. I mean, that will have different filters. In any case, I mean, right now there is no, or at least I cannot say anything from the technical point of view. This is something more political.
Yeah. Anyway, yes. So we, Borja, yeah. I mean, if this answers your question, there will be different data releases, and each will be growing in size in terms of number of areas scanned, and each will be, you know, every time possibly there will be an improved pipeline.
Sure.
Yeah, Silvia, we have a request. Can you please check the chat? We have a request from Lola.
Yeah.
The closure of the meeting is now.
We have to stop. Okay. All right. So, okay. So then we really have to stop, and we come back to this link. Okay. In 10 minutes. Okay. 50 at the hour. Okay. Sorry about that.
Okay.
Thank you. Bye-bye. There is one question, by the way, that we missed. We'll try to address this later.
Thank you. See you.
little bit to be sure that people come back. So yeah, let's wait 10 minutes, okay? I'll add it in this chart.
Hello.
Hello. So yeah, we were delayed. There was a delay in everything. So we start again in 5-10 minutes. Hi, Renato. Rosa, it seems actually. Again, so we had to disconnect because they were ongoing the final remarks of the SEA meeting. So we had to leave room. They just finished. So let's wait a couple of minutes and then we restart with Jpas Science. I hope you can hear me.
Yes.
Thanks, Carlos. Thanks. Rosa, given that we have a couple of minutes, did you want to try sharing?
Oh, yes, please. Let me see what I had to do. Compartir.
Yeah.
You hear my...
Yeah, we see it. So then if you put full screen. O ver, maybe ver arriba.
Ver, sí.
Modo pantalla completa, quizá.
Eso, sí. Okay.
Eso. Perfect.
I can move it. Okay.
Perfect.
Hi.
Hello.
I have to stop sharing.
Yes.
Silvia,
Hi,
am I the
Valerio.
next?
Sorry?
Carlos and I are Carlos and I the next one?
Yes, you're first.
Oh, sorry. I lost.
So you have to go. Rosa, I don't know if you find again the thing.
No, sorry.
I'm not sure. Okay,
Okay,
I think now it's fine. Okay, good.
No, deja de compartir como es.
Okay, I see the number rising, so I think people are coming back from the final remarks.
Are you still seeing my screen?
No. It's okay now. Thank you, Rosa. Okay,
I had a quick lunch.
Already 10 minutes lunch. Yeah, so actually Saulo wrote to me that he was cooking while listening to us. So
Yeah.
all the Brazilians have their lunch.
Yeah, I have to cook, but I'm here.
Okay, good. Yeah, you can, if you manage to cook and not burn anything, go ahead.
Oh, it's okay.
All right. So the order is we typically go, for many things, we typically go from the local universe to the furthest universe. So we decided today to do the opposite. So we start with large-scale structure and clustering, and then we move to the stellar objects, and at the end, and also stellar and variable objects. So I don't know, Valerio, if you want to start sharing. So Renato says he doesn't know. Okay. Yeah, so go ahead, Valerio, go ahead.
So I will present the first slide, then Carlos will take over with the final ones.
Okay.
We do a joint presentation. Let me share. Well, let me share all of it, easier. So I guess, can you still see?
Yeah, we see it full screen now. Thanks.
Okay, perfect. So let's wait for Carlos. I don't know if he's back already.
I don't see him. Carlos? In the meantime, is there any question? I actually, because I disconnected, I cannot see anymore the questions that were in the chat before. So if you remember them, or if you want to ask, just feel free to unmute yourself. Okay. Well, let's wait 1 more minute, and then maybe you can start, Valerio.
Okay.
Valerio, if you don't have more than 40 slides for 5 minutes, it's not decent.
I'll show you my FPS, frame per second marker.
Silvia, thanks for saving my life.
Oh, no problem. That's why we are doing backups, right?
Fair.
I also put my slides in the Google Drive because when I'm at home and my connection, let's say that it fluctuates, especially because it's raining now. And there is this correlation between rain and bad internet.
Okay, so I think we should start, otherwise it gets too long. We were already supposed to start 15 minutes ago. I don't know where Carlos disappeared. Maybe
I'll send him a Hangout message.
Yeah, I'll send him a WhatsApp, so he will be cornered by.
Or possible way. Okay, he saw my message.
Okay.
He's logging in.
Well, otherwise, either you start or we start with the theory group. But I guess I don't know, Antonio. If that would be fine. Or
Yeah,
if you
for
would
me
prefer.
it's fine. I mean, it's up to you.
Yeah. Okay. Yeah, I'm not sure whether. Yeah, I guess.
Carlos just joined.
Okay. Okay. Carlos, are you there?
I just arrived.
Okay, we should start then. Okay, let's go ahead.
Sorry.
Go, Valerio.
So let me let me first introduce Valerio. Valerio Marra is the co-coordinator of this large-scale structure group. He sent me his CV this morning, but I don't have it handy now. So he did his PhD in Padua, right, Valerio? And then, sorry, and his undergrad there too. And then he had a postdoc, if I recall correctly, in Heidelberg in Germany. Went to Finland. Then, yeah. So,
yeah,
sorry,
I spent some, no, it's okay. It's okay. I spent some time in Chicago, then in Finland, Germany, Rio de Janeiro, and then finally in Vitoria.
You are an associate professor at Universidad de Espírito Santo, right? In Bahia, right? In Brazil, right?
Espírito Santo.
Espírito Santo, right?
Yeah.
Okay. Yeah. So Valerio,
actually,
he's gonna. Yeah.
Sorry. If you guys if you wanna put the video when you speak.
When you talk, okay. I put the video to switch it off, just because Valerio will actually be introducing the very first
but
slides,
my camera is off because.
Okay, don't worry then. Okay. I mean, if you want and you can, put it. Don't be shy. But if you have any problem, don't worry about it.
So okay, yeah. So I'll shut up now. Valerio will introduce, and then I'll talk at the end. Okay. So Valerio, all yours.
Okay, thank you, Carlos. So I'll briefly start presentation of the large-scale structure group, and Carlos and I are coordinating it. And so let's get started regarding our ongoing activities. So we have weekly telecoms so if someone is interested in joining our telecoms, they happen on Tuesday at 4 p.m. for Spain or 11 a.m. Brasilia time. So right now, what we are doing, of course, we plan to do many things in the future, but what we are doing right now at this moment is an effort to produce galaxy mocks on one side, and on the other side, a characterization, identification of cosmological tracers such as LRGs, ELGs, and quasars. Now, the characterization of LRGs and ELGs was mostly performed by the Galaxy Evolution Group, so I think they will talk about that. And while the identification and characterization of quasars is mostly an effort led by the LSS group. In particular, we have been building, so we are an aim also, we're not done yet. So we aim to build big synthetic catalogs of LRGs, ELGs, and quasars. I mean, with the full synthetic J spectra. And this is one of the main motivations is to train and test machine learning codes for photosynthesis estimation, and also other alternatives. So Carlos later will discuss a little bit the quasar part. So what about galaxy mocks? So our aim here is to produce as realistic as possible galaxy mocks. That is, galaxy mock is a simulated catalog of galaxies that we think Jpas will observe it in the future. And in order to do so, we aim at reproducing with these galaxy mocks the observed densities, galaxy densities in mini Jpas. And so here I'm showing a plot that you can find in the introductory mini Jpas paper that appeared in arXiv, sorry, a few days ago. And here you can see the number densities of galaxies as a function of redshift. And you use in black, you see for all galaxies, for all odds, all possible odds. So as Silvia mentioned earlier, odds is a parameter that we use as a proxy for the redshift accuracy in the photosynthesis determination. So you see when you use all galaxies, we reach number densities that are basically the same order of magnitude of pencil beam surveys such as Alhambra and Cosmos. Then in this plot, we're also splitting between blue and red galaxies. and using also different CATSI nodes. So for example, if you consider the black circles with the CATSI nodes above 0.6, that means a better photo-Z, then you see that still we have a very high density of objects, much larger than, for example, OZ and CMAS from SDSS, and comparable to DESI. Okay. So our aim here is to build these mocks matching these abundances, and we want to do this in 3 possible ways in order to have both complementarity, because every method has its own pros and cons, and also robustness. So, so we have a phase 1. So phase 1 is to produce dark matter halo mock catalogs. And so we want to produce 1,000 mocks for each method. So to do so, we cannot use really an n-body simulation, so we use approximate methods. We want to simulate an almost full survey, so about 6,000 square degrees. So the first method will be used in Pinocchio, which is a Lagrange perturbation theory code that is used in Euclid. This effort is led by Thiago Castro. Then another 1,000 mocks will be produced using X halos. It is an exclusion set LPT code that was developed by Rodrigo Vojvodic, and was also leading this effort. And then finally, another 1,000 mocks using BEM, which is it's a parametry-free method that uses, it tunes its methodology, it is tuned on an actual n-body simulation, and it uses this tuning in order to produce very realistic halo mocks. And this effort is led by Andres Palaguera and Antolines. So in order to do so, to produce 3,000 mock catalogs, so we need computing time. So Miguel Quartin led the proposal at the Santos Dumont supercomputer, a Brazilian supercomputer in the state of Rio de Janeiro. And on April, we were awarded almost 2 million CPU hours. And this will be enough to, basically we were awarded all the hours that we asked for. And so far 400 mocks have been produced. In this plot, I'm showing the minimum halo mass that we are keeping in the simulations as a function of redshift. And this is again, is based on those mini Jpas number density that I've shown before. Here I'm showing just for show, there was a quick animation made by Thiago Castro. So this is a spherical cap. This is one of our light cones. So these are 6,000 square degrees, and a spherical cap of radius 45 degrees. And this animation is going through this light cone. So you can see the contrast, and you can see filaments, and then anyway, this is just a foretaste of what to also regarding these mocks. And thanks to Thiago that made this quickly. And so phase 2 will be populating these halo catalogs with actual galaxies in order to resemble again a real galaxy catalog that will be observed. And to do so, we're going to use halo occupation distribution, halo abundance matching techniques against that going to be tuned to the mini Jpas number densities and mini Jpas observation in general. For example, in order to characterize the different galaxies, we are using the output from Amico. I believe Matteo Maturi will talk about it during the cluster lensing group section. And here I'm showing a plot by Rodrigo von Martens, where we already working on the Amico output in order to identify central galaxies and their distribution in magnitude. And so once this phase 2 will be completed, then we're going to have really 3,000 galaxy mocks. And we are even considering the possibility of producing non-lambda CDM mocks, so that to also consider to have a fiducial model, which is away from the standard cosmological model. Here in this table below, I'm showing just the number densities for different cuts in redshift precision and redshifts. Okay. Again, for details, you can see the presentation paper. Science, of course, once these mocks will be produced, we can do really a lot of things. First, during the production, we'll prepare and validate our analysis codes. So the idea is that we're gonna not test the same codes on different mocks to see consistency between mocks, and also different codes on the same mocks to check consistency regarding codes. Once we do this, once we estimated the covariance matrices, for example, for large-scale structure estimation, for HOZ or angular diameter distance estimation, then we can really produce realistic forecasts for any, say, smooth extension of the standard model of cosmology. And that's as a time scale, we wish to start looking into it by the end of the year. Here I'm showing again the plot that Sylvia showed that just give you a feeling of how good is mini Jpas in tracing the large-scale structures. Regarding science, we have key projects that aim to extract cosmological informations from BO, from multi-tracer techniques, using directly the cosmic web, new techniques such as angular redshift fluctuation, and even intensity mapping. And now I leave the word to Carlos.
Hey, Valerio, please don't stop sharing. Yeah, don't stop because it's maybe easier if you keep sharing your screen so that we don't have to switch that. Okay. Yeah, so the group is also working on the few items that Valerio has introduced. One of them was the identification of sources that could be useful from the cosmological point of view. Some of them were the blue and the red galaxies, the luminous red galaxies and the mission line galaxies, which have been already identified by the Galaxy Evolution Group, by Rosa and Luis and many other people around. But one of the pending issues is how to actually use quasars as cosmological, as a cosmological probe. And for that, Jpas has a peculiarity because of its narrow bands. It should be, and it's performing very well in this sense. It's a good experiment to actually identify a massive amount of quasars, right? Because of the narrow bands, it can easily isolate bright, broad emission lines, which are typical for these sources. And this, as I'll show next, and this has attracted the attention. The first idea on using these quasars as cosmological probes was by Raúl Abramo from a paper in 2012, already 8 years ago. And there's a working group around this, and actually there is a MOU with the WESO collaboration, so that we can optimally extract the science associated to these objects. I'm not sure if this is actually going to be addressed in a later session, but anyway, I just wanted to introduce this. So one of the hot topics where people within our group are working currently is in the actual identification of quasars in this in the mini Jpas data samples, right? So this is the first slide. Yeah, so can you go to the previous slide, Valerio, which is probably, this is one step beyond I wanted to go. Can you go? Yeah.
The previous?
You have the previous one, yeah, that one. Yeah. So as I was just introducing, mini Jpas is just an ideal test bench on how, just to show us how useful Jpas will be in terms of isolating and discovering new quasars and how feasible it is to do cosmology with quasars. So right now we have a group of 3 different groups of people applying machine learning techniques, trying to isolate quasars from mini Jpas data. And this is Carolina Queiroz on one side, Ignacy Perlar-Fols, and then Ginés Martínez Soareche. And I hope I'm not missing anyone. I might be. If I do that, if I'm missing anyone, I apologize beforehand. But these people are combining their machine learning methods to, they are calibrating them differently. Carolina Queiroz has produced a set of very realistic mocks for the quasars, which should incorporate the realistic noise levels in every band of Jpas. And this is those mocks are being used to calibrate these machine learning methods. Independently, well, fully independently, because eventually I will be using their mocks too. and we'll be comparing methods too. I have implemented a template fitting method, which I simply just take a typical spectrum for one quasar, and then I split the spectrum into the continuum and the emission lines, like I do a Fourier transform, and then I do separate fit just to account for the possible different slopes of the continuum of the quasars. And then I have applied this on mini Jpas data, and I have recovered and then we can compare the amount of quasars that we recover from the amount of quasars that are known to be there from other collaboration, mainly from Sloan. And this way, I have a candidate of quasars. Some of them are confirmed quasars. Some of them are candidates for new quasars. And with all these candidates, and taking into account the error in the redshift, I can produce an estimate of what is the number density that for mini Jpas on this type of objects. And if you can just go to the next slide, Valeria.
Yeah.
Carlos, in the meantime, sorry, we are running late. So
sorry, I'll quick up. I'll need a minute. I'll need a minute. So this is just this, right? So this is just a comparison of a very preliminary estimate of the number density of quasars from mini Jpas compared to EBOS, the data release one. So the field blue squares are what we recover from mini Jpas. So we are simply recovering, the amount of quasars that EBOS is detecting at around redshift 1. As we move to higher redshifts, up to redshift 3.5 or so, I think you should believe this plot up at least up to redshift 3.5. Then, we seem to be recovering more quasars. Jpas is supposed, because of the power that I identify in these emission lines, we're supposed to be better at higher redshifts up to 3.5 and also at lower redshift. Although at lower redshift, we might have confusion with other type of galaxies. Anyway, and then I wanted to show you in the very last slide, just a few seconds to show. So we have some new candidates, some candidates for new quasars that have remained undetected to date so far. These are 4 examples. I have around 10 with high confidence. These are actual real quasars. These are all objects at the magnitude level of between 21.5 or 22 or above, right? And they can be identified because of the broad emission line pattern that they have. So yeah, there's a lot of work on this, and we have to make progress, and maybe put some publication out in the next 4 months on this topic. And with this, I'm done. Sorry, Sylvia, for being late.
Okay, great, thank you. Yeah, no, we have to be a bit sharp because we are already 20 minutes late. So okay, thank you, Valeria and Carlos. Yeah, is there any question while Antonio and the theory group start sharing their screen? Does anyone have a question for Valeria and Carlos? By the way, it was Natalia also searching for quasar. I thought I mentioned their name, Natalia Villanova. Just,
sorry for that. Yeah. Sorry. Yeah. I was sure I was forgetting some name. Yeah. Sorry.
Is there any question? Okay, feel free also to add in the chat, and then Carlos and Valerio can also reply directly in the chat, okay? So Antonio, to you, maybe in 10 minutes, I'll say something so we are, you will have to wrap up.
Okay, so can you hear me?
Yeah, but we cannot see.
You cannot see?
We see a green thing.
Okay.
Yeah, we see it when it's not full screen.
Okay, just a second. Now?
Yes, now yes.
Okay, fine. So, okay, I'll be talking about the Jpas Science Working Group on theoretical cosmology and fundamental physics. I will present the main scientific objectives of the working group, and also the activities that we have been doing in the last couple of years. So as you have seen in the previous talks, Jpas will be able to map the position in space of millions of galaxies and quasars over a cosmological volume. And this we allow not only to determine the distribution of matter on large scales, but what is more important from the cosmological point of view, the time evolution of these structures. This, as we will see in a minute, will allow Jpas to determine the expansion history of the universe, the growth rate of structure formation as a function of redshift, and this will provide very useful information about cosmology, but also about fundamental physics. In particular, we will see that Jpas will be able to give information about the nature of the dark sector, about gravity on large scales, and also on other aspects such as inflation or neutrino masses and so on. So before we move to these science objectives, let me introduce the working group. So these are an incomplete list of members of the working group. We are still updating this with the new members. So we are now around 40 people in the working group. So this is the organization of the working group. All the information I will give in the talk can be found in the wiki page of the theory group, which is shown here. And communication among the members is through the Google group in Jpas theory, and the coordinators, as you may know, they are James Alcañiz from the Observatorio Nacional in Rio de Janeiro and myself. So these are the key projects in which the working group is working. I will show very briefly the title of each key project and the leading person. Some of them are coordinated with the LSS group. For example, the first one about the reconstruction analysis led by Francisco Quitaura. This is the aim is just the reconstruction of the real space position of galaxies, taking into account the effect of photometric errors and redshift speed distortions. And the second one is led by Raúl Abramov, and the aim is just to use the multi-tracer approach to large-scale structure, and in particular to the biospectrum. The third project is on the physics of inflation, and led by Enrique Martinez González and Nicole Benetti. The idea of this key project is just to constrain models of inflation using both Jpas data and also combination with CMB temperature and polarization. The other aim of the project is just to prove primordial non-Gaussianity using, again, the same type of data. Then we have the project led by Saulo Carneiro on interactions in the dark sector. The aim here is to use Jpas data, lensing and large-scale structured data in order to detect or constrain possible interactions within the dark sector, dark matter-dark energy interactions, and also the possibilities of interaction with the visible sector. And then we have the fifth project led by Jason Alcañiz, Shinji Tsujikawa, and myself on the modifications of gravity, and also on dark energy, alternative dark energy models. Here again, the aim is just to use Jpas data to detect or constrain possible deviations from general relativity on cosmological scales. The sixth project is led by Carlos Hernández Pontagudo, and on the possibility of using or combining Jpas data on large-scale structures with CMB in order to reconstruct the gravitational potentials and peculiar velocity fields from this cross-correlation between the two maps. There is a seventh project led by Carlos Bengali, Armando Berniu, and Valerio Marra on the cosmological principle. The aim here is just to find null test of the Friedmann-Lemaitre-Robertson-Walker geometry, and also to measure the cosmic homogeneity scale using different tracers, and also test of statistical isotropy using different tracers. And finally, we have an eighth project, which is also coordinated with other working groups, which we call miscellaneous projects, which include 3 sub-projects, which are just the constraints on massive neutrinos using large-scale structure and cluster data, led by Raúl Angulo. The velocity fields from luminosity fluctuations, also led by Raúl Angulo, and the possibility of observing strong lensing of quasars by Valerio Mar. So these are the key projects ongoing, and now we go to the results that we have obtained so far. The working group has published 2 papers in the last years, both in monthly notices. The first one is this one here on the forecast on interacting dark energy from baryon acoustic oscillations and redshift speed distortion, which has been led by André Costa. And the aim of the project here is just to try to determine the sensitivity of Jpas in order to measure the coupling between this chi coupling here in the left plot, the coupling between dark matter and dark energy. As you can see in the plot, the full line represents the confidence, the 1 sigma confidence region for the full survey, for the full Jpas survey. And it will be able to measure this parameter with precision around a few percent. These are just Fisher forecast estimation. So this is only a good an order of magnitude estimation of this of the precision of these parameters. And then we have we can compare with other surveys like DESI or Euclid, and as you can see here, the precision of Jpas is comparable to the DESI for this particular parameter. On the right plot, you can see the accuracy that for the same parameter on different redshift bins. And again, you can see that in the low redshift regime, say below 0.6, 0.7, Jpas reaches similar precision as other surveys. We will see this in more detail in a minute. The second paper is another forecast paper on dark energy and modified gravity theories, led by Miguel Aparicio. And here the aim is just trying to test the sensitivity of Jpas to the equation of state of dark energy. In this case, in the left plot, you can see again the confidence regions for the equation of state parameter of dark energy and the time dependence. Again, for Jpas in the solid line and other surveys, just for reference. You can see that for this parameterization, Jpas will be able to measure the equation of state with a few percent precision, again similar to DESI. And on the right plot, you can see the precision with which Jpas will be able to measure the Hubble parameter as a function of redshift. So again, you can see what I mentioned before. The full line corresponds to Jpas, and you can see that at a low redshift below say 0.6, 0.7, the precision of Jpas will be comparable or even better than the other surveys, and in both cases around a few percent. This is even more clear in these plots about the precision for growth function, F sigma 8. This is again a Fisher forecast estimation. And here you see again for this parameter as a function of redshift, Jpas will be able to measure at low redshift with a precision around 1–2%. And if you compare with the other surveys here, for reference, I plot just DESI in blue, Euclid in yellow, and the dotted pink is LSST. You see that the best, the optimal window for Jpas is this region below redshift 0.6. Finally, it is I show also as a comparison of the accuracy or the precision for the matter power spectrum for Jpas and other surveys. Again, you can see that the maximum precision is achieved for scales around 0.2 H inverse megaparsec. Almost for all the surveys, the best, the most precise region is this. This depends essentially on the volume of the survey, and again, in all the scale range, all the surveys are very comparable. So this is all. Thank you.
Great, thank you very much, Antonio. Any question for the theory group? I know it's not so easy to ask a question in these forums. Again, we can also come back to questions later. So also feel free to raise your hand. Actually, I see a raised hand. Sorry, I didn't realize it until now. Martin?
Yeah, I have a question, but I can't wait until the end because it's.
No. Go ahead.
And it's quite a general question, so maybe it makes more sense to, or maybe it is answered at the end. So whatever you want to add.
Go ahead.
Okay, so maybe it's a silly question, but I would like to know whether there is already defined a strategy to deal with the systematic effects, in particular with observing conditions, especially taking into account that you have mentioned studies about primordial non-Gaussianities and large-scale structure studies, because some of the observing conditions could produce a signal that resembles what you expect from primordial non-Gaussianities. I mean, just to know whether how do you deal with observing conditions?
So in principle, data is taken during photometric nights when the observing conditions are optimal, and the seeing, I forgot what was the threshold, below 1.1 or second. Someone can correct me. Now, I'm not sure specifically on the issue you're talking about, the connection with this primordial non-Gaussianity, how that could influence. I see Jesus unmuted himself, so maybe you want to comment?
Yeah, I mean, regarding with this now in the UPAT, we are working in developing a tool to construct, by demand, on demand, maps of this kind of any, in fact, of any parameter of the sky, and with the idea of providing also these maps in we are thinking in Mango, so people can use this data to take them into account in the analysis. This is something that we are working. I mean, right now it's still a work in progress, but the idea could be this one. It has two. I mean, okay, the goal is twofold for us. For the, let's say, for the observational point of view, to check if there are some issues with the observations, detect them, but also from the point of view of the scientific exploitation, to provide to the people, to the researchers, a tool to get this kind of all sky survey maps of whatever information we could have stored. Well, I don't know how this information is going to be used, but we are thinking to make this for in principle also for this kind of analysis of systematics at the level of cosmology.
Okay. Thanks a lot.
Thank you. Anyone else?
Let me simply stress that these maps that Jesus was talking about will be extremely useful in terms of tracking systematics, particularly on the largest scales. Right? So this what Jesus was saying. I hope it will be either in Mangle or in Hilpix format, but this absorption, extinction, seeing, air mass, these things are necessary in order to track these systematics. Right?
Thank you.
Sylvia?
Wonderful. Yeah.
Just to comment that there is another paper from the theoretical group to appear in the next days. Jason is finishing the draft to circulate in the theoretical group, then in the collaboration. There's another paper with a forecast for unified and interacting models.
Okay, great. Okay. Good. I don't see any other raised hand. If there is anything else coming up you want to mention or comment, just write on the chat or later. And then now we pass to clusters, cluster and lensing group. Renato, you're there? You share?
Yes, just a second.
Yeah, great. It's working now. Before we couldn't hear you.
Can you see it?
Yeah. Yes. So go ahead, I'll let you know when after 10 minutes, okay?
Sure. Okay. Well, hi. I'm not sure this is just a Jpas meeting. They're outsiders, but if the outsiders, and my name is Renato Lubke. I'm from the National Observatory of Brazil. I'm one of the coordinators of the science working group of cluster of galaxies and lensing, together with Chema Diego and Eduardo Cipriano. I think both are here as well. I'm going to be, in the very short time that we have here, I'm going to be very briefly brushing through some of the developments in preparation for the Jpas data to come. And I'd like to reserve most of the time for the presentation of some of the concrete results from the Jpas paper in terms of the cluster catalog. With Matteo Maturi, who will continue after me. So, well, for those that do not appreciate clusters as much as I do, clusters of galaxies, they sit in a very interesting spatial scale where you can go in and study all kinds of rich phenomenologies that you have in clusters in all three components, mass components in galaxies. You can study different evolutions of galaxies there, and I think Raza probably will talk a little bit about this very soon, and stripping of stars that create ICL, and that is one of the interests of our group as well, is being worked on. And sometimes the gas strip falls into the intracluster gas, where you have this plasma that has tens of millions of degrees and has all kinds of magnetohydrodynamical phenomenologies that people study, shock fronts, cold fronts, and so on. That we're not going to see with Jpas, but we're going to see with partner space missions as well, and dark matter. I have to remind you that the first time that we actually saw dark matter was in a very clever combination of optical and X-ray studies using weak lensing. And so if you go to a larger scale, since clusters are the largest gravitationally connected systems in the universe, they're considered as fair samples, and people can use clusters to determine or to constrain cosmological parameters. Let me see if I can change slide. Did it change?
Yes.
I'm assuming
yes.
it changed. Okay.
Yes.
And the most classic way of determining constraining cosmological parameters with clusters is through the mass functions, the number of clusters you have over a particular threshold per redshift. If you do this, you can constrain omega m, sigma 8. If you look at this with how it evolves with redshift, you can get information about the equation of state parameter for dark energy. And the edge of Jpas, of course, in clusters is the high precision photo Z's, which makes detection of clusters a very much more trivial system, because you don't have to worry so much about foreground and background galaxies. And because of that, you can go to very, very small systems, like groups of galaxies that have been notoriously understudied because they're very difficult to determine membership and so on. So a lot of the effort so far to try to use clusters cosmology has been in getting masses. They're well determined. And there is a lot of effort in the cluster group to determine masses. Of course, first you have to find the clusters, and Matteo is going to talk some of the results of the 3 different methods we have been using to find clusters and find groups. But also trying to find independent methods to get the masses. And there's a group studying photovelocity dispersion. Velocity dispersion is one way of getting dynamical masses of clusters. And the precision of Jpas is so good that we hope that we can, at least for high mass systems, determine independently velocity dispersions from the photo Z's. And of course, the natural way, the most basic way, is through richness and scaling relations that involve different wavelengths. And also with weak lensing, which is going to be a big part of Jpas. I'm just showing here one plot that Eduardo Cipriano sent me, where it places, here's the limiting magnitude, and this is the area covered. Since Jpas covers a very large area with very good quality, it sits in a pretty competitive position with respect to different surveys. And at least I hope, maybe Eduardo later is going to yell at me, but I think that at least in a stacked way, we're going to be able to get independent measurements of massive clusters there. So getting to groups, of course, there are many other different sciences that different people's interest they're getting ready for, like getting a very precise 3D cosmic web kind of structure that Paco Quitaura is working on this, and compared to simulations, we can constrain cosmology with this, and we can do also science in terms of, for example, detecting the WIM, the intergalactic medium, through, for example, absorption systems in the background. And there are different sciences that it will take too long to go through, that there are people interested in the group. So going to what I mentioned before, one of the things that I think is very exciting is the ability of Jpas to detect very low mass systems. And this is a prediction that was done before we had any data at all. Begon Escaso, and where you see here is the limiting mass detected and the redshift. And you see how it compares to the ACT or the Cepheid telescope and LSST and in Rosita. And Jpas gets down to here was 5 times 10 to the 13th. This was limited basically to have 80% purity and completeness. But of course, it can go lower, and Matteo is going to go into that in a second, but it has a very, very good match, especially for redshifts, intermediate redshifts, to get studies of groups. So I think I'm going to leave most of the time now for which is not much, for Matteo to talk a little bit more about some concrete preliminary results from the Jpas data.
Okay, so perhaps I can share my screen, but first I need to unshare your.
Okay. Stop share. Okay. Should be with you.
Yes. Can you see?
Yeah.
Yes.
Okay, cool. So this was the last slide of Renato from this Move On. And these are basically the promises of mini Jpas with respect to the detection of clusters and their use for cosmology, and then further astrophysical topics such as galaxy formations, for instance. And you can see that the promises were giving detections rates down to masses close to 1 to 10 to the 13 solar masses, 5, 10 to the 13 solar masses. So pretty small objects. Let's see if we manage to keep these promises. And let's move on. Okay, so these are the 3 algorithms that we are using to detect galaxy clusters. So the first one is the Voronoi tessellation, which has been run by Paulo Lopez. And the idea is to use a tessellation of the sky, so the catalog of galaxies, and say it is a grid which is shapeless. The shapeless grid is adapted to the density of galaxies, and for an optimal identification of overdensities. These overdensities are identified as galaxy clusters. You can see here on where the arrow is pointing for various points that have been identified in the Voronoi tessellation on the left-hand side. The second method is PZWAV. This is one of the algorithms used within Euclid. And Lia Dobrova, Eduardo Cipriano, and Anthony Gonzalez are running the algorithm. And on the right side, you can see the footprint of mini Jpas. So this is an actual slice in redshift. So just imagine to observe along your mini Jpas sky. And just imagine a slice in redshift. I think this was redshift 0.24. Okay, so let's say intermediate low redshift for our survey. And the filtering approach here is composed by a wavelet, which maximizes the signal to noise ratio by trying to suppress the contribution of the large scale structures. And again, you can see that how clusters are enhanced as overdensities. The last method is AMICO. It stands for Adaptive Matched Identifier of Clustered Objects. This is this is the other algorithm used within Euclid. So we have the two algorithms that are used within Euclid for Jpas. That's very good because it will help to also compare the two surveys. And here the method is different with respect to the previous ones, in the sense that one has to assume a model for the clusters, for example, in terms of luminosity distribution of the galaxies, and in a radial distribution of the galaxies within the clusters. And then the algorithm maximizes the signal to noise ratio and adapt itself such that to maximize the detection ratio of your algorithms. And again, you can see the same footprint for the same redshift as that I've shown before for PZWAV. So you can see there are the same structures there, but of course the filter is seeing the galaxies in a different manner. Okay, so these are the three algorithms that we are using. Here is few examples of clusters that have been detected in mini Jpas. So you can see a very nearby one, redshift 0.08 in the top panel. Then an intermediate cluster, redshift 0.27, and then one which is rather far away at redshift 0.68. So you can see, just to give you a glimpse of which kind of clusters and structures that we are going to detect in our data. Of course, detections is the starting point. Then what we could do is to use, for example, AMICO to associate a probabilistic membership to the galaxy. So for the overall survey, we are going to know what is the probability of each galaxy to belong or not to a certain detection. Here you can see one of the large detections that we have, and in yellow you can see those galaxies that have a large probability to belong to clusters, and then down to degrading to darker colors, lower probabilities. This is very important, and it's very good to see how our probabilistic association compares with spectroscopic association. And you can see this in the top right panel, where you have the probabilistic membership given by AMICO on the x-axis, and the probabilistic association given by spectroscopy in the y-axis. Of course, the ideal case is that the line goes along the diagonal, so this would be perfect match between the two methods, and you can see that there is a very good agreement. So you can see that the spectroscopic redshift that mini Jpas and Jpas is going to provide, we are going to provide very solid probabilistic association. It is open up a lot of perspective for galactic studies and so on. Here is few other characteristics that we can, other parameters that we can get from our clusters. So top left panel, you can see the accuracy with which we can identify the location of clusters in redshift space. And you can see here, you can see the sigma is 0.0028. That's a factor of 10 better than what I could do with kids. So that's a factor of 10 better in terms of redshifts. This opens up the possibility of making clustering with galaxy clusters. And again, another, and also allowing us to have another further cosmological constraint. On the right-hand side, you can see a scaling relation between the amplitudes. So this is just one of the outcome of AMICO, for instance. So that's one of the algorithms that we used, and the mass obtained with X-rays. Therefore, we can then calibrate our mass proxy based on optical observations with, for example, X-rays observations in this case, and then have a link between what we see in our data and an actual mass for the halo host in the galaxy cluster. And this again is key when we want to do cosmology. Then of course we have richness estimates, so the amount of galaxies that belong to clusters in the top left corner, where I have the mouse. And you can see the promise that we have kept our promise in terms of mass selection in the bottom right corner, where you can see the mass along the x direction and the redshift along the x-axis. And these are the masses that have been detected with AMICO in the mini Jpas. And here again, masses are again based on X-rays. And basically you can see that we can go down to basically 10 to the 13 solar masses in terms of mass, which is basically better than what we expected in the forecast. So the survey is going to be very competitive. It's going to be very competitive. Another thing that we can do is again based on the photometry of mini Jpas. We could use mass light trace approaches to determine what is the strong lensing features that could be provided by the clusters that we detect. Here is an example and where I showed three different critical curves. So these are the areas where we expect to have strong lensing features. Okay, so we're going to provide this sort of information based on the spectroscopy only. Then we have, as I said, having a probabilistic association of the galaxies to cluster. We can then probe and investigate what is, for example, the mass of the galaxies, what is the age of the galaxies, and so on and so forth, to dig down into galactic evolution. Moving on, last stage will be when we are going to have, this is what we expect for Jpas, when we are going to have a large portion of the sky. We are going to count basically galaxy clusters across the survey. Once we count the galaxy clusters, we can correct the counts we have with the selection function of the survey. And with that, we can link basically the mass function that we expect from theory, naming how many galaxy clusters we find with a certain mass at a certain redshift, with those that we observe in our survey. And then with this, obtain cosmological constraints. As a teaser, in the bottom panel, you basically see what we achieve with kids. So these are different surveys, but I expect that we are going to get constraints that are better than these ones, because what I'm showing here is based on 370 square degrees, so a pretty small patch of the sky in comparison with what we are going to obtain with mini Jpas. The difference is that kids is a little bit deeper, but has a much worse spectroscopic redshifts, as I discussed before. So I'm pretty sure that we are going to do better than that. And you can see that already here we have constraints on sigma 8 and omega m, which are competitive with Planck and the WMAP. So stay tuned, because cosmology with galaxy clusters, and in particular with Jpas, are going to be very interesting. And I stop here. Thank you.
Wonderful. Thank you. Thank you, Renato and Matteo. Yes, this is very, very promising. It's really amazing to go well below 10 to the 14 solar masses in cluster mass, right? And actually getting really close to 10 to the 13. Is there any question? I don't see raised hand. Someone has any question or comment? Okay. Anyway, I think you know, for we'll probably have out, right, Matteo, the cluster catalog soon for mini Jpas.
Yes, the three catalogs are there, and we just need to make some polishing, then derive the scaling relations, and then we are ready to start to deliver to the community if this is needed. Right.
So we'll have the we'll have out the proof that really Jpas is very strong in this aspect. Okay. Given that we're running late, if there are no urgent questions, then we can move on. Thanks, the cluster group, and then. Thank you. And then we move to galaxy evolution to Rosa. Yeah, I haven't been very good with the timing. I'll try to tell you after 10 minutes, okay?
Hello?
Hello. Yes, we can hear you, Rosa. Can you maybe try to put it full screen?
Yes, I need to see. Okay?
Yes.
Can you see?
Yeah.
Okay. Well, it has been very exciting today with the press release of the fair image of the GPCAM. They show the N31 filling the 14 CCD. The images, in fact, tell us which is the power of Jpas for galaxy evolution study. So this is the goal of this 10-minute explanation about the working that we are doing in the Galaxy Evolution Working Group, which is to show you which is the power of Jpas for this Galaxy Evolution study. Ariana Cortesi from the Observatorio Balongo in Rio, and myself, we are coordinating this study in Jpas. Let me start to say that in fact, Jpas is a perfect survey for Galaxy Evolution study because because we can have the observed optical range covering every 100 angstrom for the filter system. We can study the cosmic evolution of the galaxy population and property and how it is evolved with the RC. So it is also very good survey for estimating or detecting emission line, sorry. It was a very good survey for detecting and identifying emission line galaxy and study the cosmic evolution of this galaxy, because the full we have maximum of the filter is only 140 angstrom, so we can detect it a lot of objects with the emission line. And also, I will show you later, it is also a perfect survey for IFU light study, because we have a camera with a very good pixel size, which is only 0.23 arc-second per pixel. So that means that we can study not only the property of the galaxy in the central part, but we can also build how changing the property with the radial distance. And also the Jpas is a very good survey for study the color variation of the morphological parameter. And on top of that, we can say that this is perfect survey for environment study, because we will expect it to cover a lot of area in the sky. So that means that we can sampling the filament in the cosmic web, where could be for the cluster of galaxy and group, but also we can pick at a galaxy which is in more isolated environment. So we can study which is the role of the environment in the evolution of galaxy. Now what I'm going to show you is the result that we have already obtaining analyzing the mini Jpas data, and to show in fact that we can get this goal that I had explained before. That's an example of the galaxy that has been observed in mini Jpas. This is represent a different area of the Aegis field, and you see that there is a nearby galaxy where we can identify clearly the morphology and the spiral arc of the galaxy. Even if you look at this galaxy has been detected that has a very long filament that probably correspond to an optical jet, radio jet. And also we have galaxy which is clearly in group and in cluster. So that means that we can cover a lot of variety of galaxy and environment with this, only with this 1 square degree observation of the sky. Obviously, one of the more important aspects for galaxy evolution is the fact that we can build the spectral energy distribution in the observed optical range. This is what we saw here with this example, where in color we are showing the real data from mini Jpas. On the top, there is 3 galaxies that has been characterized to be late type galaxy with H alpha emission, where it is detected in the 3 galaxies. In other, there is also oxygen 3 emission and even oxygen 2. So that means that they prove that in fact a galaxy with a nebular emission can be easily detected in Jpas. on the bottom panel, where we saw is 3 luminous red galaxy at different resi. You can see that we can go also to analyze a galaxy which is around magnitude 22 and 22.5 in the R band. Obviously, using this G spectra and combining with technique related with the stellar population synthesis, we can retrieve from the main property of the galaxy. So we can estimate the ages of the stellar population, metallicity, extinction, star formation history in general. So this is very useful, in fact, if we want to identify and characterize the luminous red galaxy and also the late type galaxy and galaxy with emission line. This is an attempt given here where we are plotting the whole distribution of result that we are obtaining analyzing the ages field. It is, we were able to retrieve the property for about 8,000 galaxy at resi less than 1 and with magnitude in the R band less than 22.5. So here it is clearly seen which is the distribution of galaxy in the blue cloud and also in the red sequence. Also the color, it is indicating which is the ages of the stellar population at what is expected. The red sequence is populated by the older galaxy. The good thing of this survey is that in fact we can study which is the evolution of this property with resi. This is what we saw here, where in the first column it is related with the galaxy that has resi less than 0.33. In the second column, in the middle column, it is galaxy which is between 35 and 0.6 in resi. And the last column is with galaxy between 0.6 and 1 in resi. So this is an example of the thing that we can do to characterize the galaxy population and how it changes with the cosmic time. So other aspect which is very interesting is to study, as has been mentioned before, which is the role of the environment in the galaxy evolution. So Matteo has already shown how to identify the group and cluster in mini Jpas. This is one beautiful example of the big cluster that has been detected in the mini Jpas. In the same way that for the general sample of galaxy, we can study which is the spectral energy distribution for every galaxy can be fit, and we can estimate which is the property of the galaxy in terms of the color, the intrinsic color, ages, and so on. That's an example of the thing that we can do. So here, what we are referring is the background is this general distribution of galaxy in the many Jpas in the U minus R intrinsic color versus the stellar mass, and the big dot correspond to the almost the 100 galaxy that has been that has probability to be in the to belong to the cluster. This is the point that corresponds to the BCG, which is the more important galaxy in the cluster.
Rosa, can you? It's been already more than 10 minutes. If you could.
Okay. Okay,
in a couple of minutes.
Okay, so Jpas is also a very good survey for detecting emission line object. This is a few examples of nearby spiral galaxy where we have detected H alpha in emission. So we can build the star formation history and the property of emission line galaxy using the tracer of H alpha line at to resi 0.2 and also the oxygen 2 at to resi 1. But also we can detect quasar and Lyman alpha emitter at high resi. This is one example of the work that is doing by Ginés Martinez Olaeche, where we have detected we have studied all the galaxy mini Jpas with resin less than 0.35, and we have estimated which is using deep learning technique, which is the equivalent width of H-alpha, oxygen 2, and nitrogen 2. This sample compared the result that has been obtained for Jpas with the result obtained for SLO, which is the green line. But also, which is very important, is that the emission can be detected not only in the central part of the galaxy, but could be traced or sampling along the radial distance of the galaxy. And also combining with the stellar population analysis as the sample here, where we represent the U minus R column versus the stellar mass, but also we can distinguish the galaxy by the equivalent width of the emission. So we can identify the early type galaxy not only by the color, but also for the emission line. This is another example of the work that we are doing, that it is identifying the quasar, and also we are measuring the photo C for this object. This is two examples, RC0.4 and RC1.7, where we detected the Lyman alpha and the carbon line. And the third point was to show you the Jpas and IFU of low spectral resolution. In particular, in mini Jpas, we were able to detect a few galaxies at resin less than 0.1. And this is one of these galaxies was already observed by the MANGA survey. And this is this is the green line, which is the spectra from MANGA, and we extracted the inner 0.1 effective radio from the Jpas data, which is the black point. You can see that the agreement between the two results is very, very nice. Also, we can estimate the property of the galaxy along the radial distance. We were able to do for extraction and to get this radial distribution up to 2 effective radio. And the advantage with respect to MANGA is that we can go further than the MANGA data, because this is the pentagon, so the field of view of MANGA, and with MANGA we can only obtain the 2 first points of this radial distance. So that means that with Jpas we can do better than with MANGA in terms of the spatial distribution. Also in terms of the color, this is an image, a plot where we show the 54 narrowband filter of the Jpas. And one important aspect is to, in fact, to study the color variation of the morphological parameter. And that's one example that has been obtained by Ariana, where they study 2 galaxies of different morphology. And the advantage is that using all the color, they can estimate in addition to parameters like the concentration index, also which is the fraction in every filter that came from the mass and from the voltage and the disk of the galaxy. And to finish, only to show you that in fact Jpas will be very good for galaxy evolution study, because I have so in the case of M31 we can study big galaxy. This is impossible to be studied with the actual IFU, which is only 1 arminic, the maximum. So that means that we can study the spatial distribution of the nearby galaxy in the nearby universe, thanks to the characteristic of the GPCAM. And also galaxy, which is more similar to Khalifa and this galaxy and MANGA. So we can study a lot of, to do a lot of IFU study. And also, of course, we can study the nearby galaxy cluster, as this, for example, show and study also the spatial distribution of property within the galaxy, and also with respect to the distance of the main galaxy. And of course, cosmological field as the example that I have shown here from the mini Jpas. And just to finish, I'd like to say that, Ariana and myself, we are coordinating the group. This is a very active group with more than 40 people involved in the design. It is very international because, and also we have the telecoms every Monday at 4 p.m. To finish, I would like to thank to the people that has participated directly in the result that I presented here, and also other study that is going on in the Galaxy Evolution Group. Sorry for to be so long.
Thank you very much, Rosa. Very nice. A lot of different things. Good. So yeah, I guess it is getting though a little late. Carlinhos was mentioning in the chat, it's good to always remember that the narrow bands will be beamed, so the effective resolution will be 0.46 arc-second, not 0.23 for the narrow bands, while while for the broadband we will keep the 0.23 arc-second.
Well, in any case, the resolution, the spatial resolution will be significantly better than any of the actual IFU, because except with Muse that has 1 arc-second for the fiber, most of them PPAC or in the manga collaboration, it is more than 22.5 arc-second per fiber.
Yeah, so really very different, even if we double, triple beam.
Exactly.
Okay, thanks for clarifying. Okay, I don't see raised hands, or there is a clapping. So there are virtual ways to interact. Okay, thank you, Rosa. Yeah, I guess we can move on given that we are late. So there are 2 groups more. I think it will be a bit shorter because unfortunately the size of mini Jpas didn't yet give them enough opportunity for performing some science analysis, but I think it's very interesting, the potential also of the stellar group and the variability group for Jpas. Okay, I see Rosa. Rosa, I see you. So, okay, great. Thank you. Not that you know, it's good to see you. So the actually, I don't know who the stellar group who is presenting.
Your worst nightmare.
Okay, Alessandro. Okay, let's see if it works or if it doesn't.
Let's see. Let's see if we're lucky. Let's see if I don't share anything which I shouldn't.
And again, I'll ask you to please keep it brief.
Yeah, I only have 41 slides though.
Okay.
All right. So I'm not talking for myself, but I have been asked by Simone and Vinicius to give this presentation on their behalf. So this is the science working group of on stellar populations, which is led by Simone Daflon from the Observatorio Nacional, Rio de Janeiro, Brazil, and Vinicius Placco from University of Notre Dame, United States. I believe Vini is actually around in the chat. He may complement, and actually he's more knowledgeable about most of the things than me. The group is built of 29 people from different institutions. Similarly to what Rosa was commenting for the Galaxy Evolution group, the group is mostly spread over Spain and Brazil with other people from Italy, or as I said, Vinicius who's in Notre Dame, and people from Tartu. The scientific goals and our science topics are varied, from white dwarfs and binary stars and cataclysmic variables. You can guess who that person is. At least the people within the collaboration know who that person is. Ultra cool dwarf stars, planetary nebulae, other Lyrae. So we cover a variety of topics. Possibly the most relevant thing, as Sylvia was commenting, is mini Jpas did not give a lot of room for entertainment because the field is relatively small, and especially if you care about relatively rare objects, you run into troubles. Yet mini Jpas is a very interesting test bench, and this is work that Vinny has been doing, as far as I understand. So those are simulated spectra of different, on the left, different carbon over iron, and on the right, iron over hydrogen, metallicity. And as you can see, that I'm not sure if you can see my mouse. Can you see my mouse?
Yes.
All right.
Yes.
So each of these is a Jpas filter. So this is a filter. This is a filter, right? And what you can actually see is that changing the carbon over iron dependence, you can actually see this line appearing or disappearing, and you can actually trace it through this specific filter in the Jpas filter system. And similarly, you can do the same game with iron. And this is basically, this is basically the most relevant thing in our historical moment, where we have, on one side we have Gaia, and the other side we have all these super spectacular post-SDSS survey, SDSS itself with apogee and blah, and then Foremost and Weave and everything. What is even cool, what is also very, very cool is you can actually put together the colors which are metallicity sensitive and colors which are, or a color which is sensitive to temperature, and you can build this kind of map, and you can identify regions, and you can actually start telling what is the metallicity and what is the temperature of a star, only using our colors. Of course, there's going to be issues with interstellar extinction, which for the moment we're keeping out. I saw this plot yesterday for the first time, and it blew my mind. And yeah, finally, there's at least 2 or 3 groups which are independently working on the spectral energy, on the SED fitting of many Jpas spectra. And I swear I had no role whatsoever in having a cataclysmic variable as the first object in the figure of the SEDs in Sylvia's paper. But you can see, and you can see the beauty of these spectral energy distributions. You can see in the hot stars, basically you can literally trace the Balmer lines, and you can see the molecular bands in the red for cool stars. So this is our gold mine, and for the time being, as I said, it's going to be mostly a test bench. And when we're going to start having the first few 100 degrees from Jpas, this is going to be a significantly different story. I guess I'll thank you very much.
Great, thanks.
I was better behaved this time.
Yeah, thanks, Alessandro, and also the coordinators and everyone in the Stellar group. Okay, let me see. Okay, I think we can move on to the last presentation, and then if there are some final questions, we can comment at the end. So Alvaro, you share, right?
Yes, just a second till I find here it is. Okay, this is going to be even shorter than the presentation.
Yeah, the poor the transient group is yeah.
Yeah.
Well, you will tell us about it.
Yeah.
Yeah.
Well, this is the two legs of the transient group, which usually has three legs with the variable stars, cataclysmic stars. But I'm going to just show a few slides about supernovae and minor bodies. I coordinate a part of minor bodies, and Beatriz Blanco from Rio de Janeiro coordinates the part of supernovae. So if you have any question, there's her email. You are seeing my screen, aren't you?
Yes, yes.
Okay. There is her email. She listed all people that at some point participated in doing anything about supernovae. Most of them are in Rio de Janeiro. I believe some people bit away from the group or hasn't participated much in last years. This is basically what they want to do with Jpas data. Unfortunately, with mini Jpas, I think it was not possible to do anything like what they had expected to do, the light curves and the classifications. For the minor bodies, it's just these people. Actually, in the web page of Jpas, it's only the first three persons: myself, Jorge Carvano, and Fernando Roig. All of us at some point at the Observatorio Nacional. And these other people that participated, but they are not listed in the page of Jpas anymore. I don't know exactly why, or they are not in the active collaboration. Javier Licandro, Dufar, Lázaro, and a few postdocs and students as well. So you might see we are badly, we need a lot of manpower, especially with the amount of data that's gonna come. We cannot do it by ourselves. I don't have any plot to show because we haven't worked with data. We've been struggling a bit with the pipeline to detect the objects. I believe it's by now almost ready. I think Georgie is in the phase of testing it, and at some point, some of us should have been to CEFCA to do the installation of the new version of the pipeline, but the COVID situation just stopped everything. So those are for the delays we're having. With the science we're aiming to with the Jpas, it's at least at the beginning limited, because we aim at serendipitous detection of minor bodies. We are going to get partial detection of photospectra because each different trade covers just part of the spectra of the objects, and we can use that at some point. The bluer filters are basically of little use for us, but we can work with the visible and the red filters. We can do something with this. We can start classifying them. It's usually done with minor bodies, and start having a map and start creating maps of compositional distribution in the solar system. But we need numbers, and we need someone to actually start digging into this data. There is an external pipeline that works fine, but I don't know. I think it's running in CEFCA, but I haven't had time to look into it in detail and see what's data is producing at this point. Other science case we are planning is doing phase curves, which is basically trying to determine how the brightness of the object changes with the phase angle. Once you remove all other geometrical effects, like the changing distances to the Earth and the Sun, and with this obtain what we call zero phase photospectrum, which can be used to templates and study effects such as the phase reddening that happens when you observe asteroids at different positions in their orbits. You get changing spectra, not because of composition, but just because how the light's being reflected off the surface. Well, if among the people that's listening here, someone interested in any of both of the groups I showed here, well, the emails are in the presentation, and if anyone wants to contact us, you can find us easily in the webpage of Jpas, and we gladly accept any help that can be provided to us. Thank you.
Thank you, Alvaro. Yes, if anyone here is listening and is interested in variable object, transient object, you know, we welcome help with that, right? That's one of the message, and yeah. And let's see also what Jpas will be able to do with that. Yeah, certainly. It's not easy when not observing all the spectrum at the same time. So there might be we need to find ways to correct for that, or how to somehow live with that. Yeah. Okay, so thanks. I think we went over all the working groups. So we have a pretty wide range of interest. I am wondering, I don't know if anyone has any question or further comments. I can imagine we're all pretty tired. Anything? Well, so let me then just well, say a few words, and then you know, if anyone else, I don't know if Javier is there. Yes, Javier is connected. Pepe, if they want also to say some closing remark. So, well, thank you very much for coming to this Jpas group session. We want to take the opportunity to go over the project, and in particular also, yeah, focus on the working group, so you have a feeling of what is going on in the different groups of Jpas. Jpas has this advantage of being versatile, very versatile, and you know, a lot of different science cases can be covered. So, you know, if you have, if any of you who is not yet a member, if you're interested in collaborating or so, feel free to contact us, to contact me, or contact Renato Duque, the other scientific coordinator, or anyone of the board, Javier, Pepe, Renato, and Raul Abramo. You know, feel free to, or contact the coordinators directly of the working group to have more, you know, more direct feeling of what, more information of what they're doing. And you know, and if you're interested in get active, you're you know, welcome to contact any of us. Okay, so you know, I think if there is no other issue, I think we can close here. Javier, do you want to mention anything?
Can you hear me?
Yes. Yeah, okay. Actually, it's good to put the video to show ourselves at the end. Yeah.
I don't know if Pepe also wants to say something. From my side, I just want to thank again the participation of the people in these sessions. I think it's important what you mentioned, Sylvia, is the fact that well, it's been obvious that the Jpas is going to provide a huge amount of data. And there is a huge amount of projects that can be done with this data set. So I think I would like to reinforce that we welcome if there is people interested in specific science cases or particular projects, please get in touch with us, because well, you know, Jpas is a collaboration, but there is ways to participate, and we are more than welcome to hear your ideas and to look the ways to work together. So I think this is one of the reasons of this meeting, not only for the members of the collaboration, but also for those outside the collaboration who could see the potential of this project and who get interested in working with us. From my side, not much to say. I think I think we all are aware that we are in a very interesting times. I mean, we don't only have real Jpas data provided by mini Jpas, as you could see, but also, well, JPCam is a reality. You have seen at the beginning of the session the technical first light of the camera, and the results are so promising that I think we all are very happy, and we are looking forward to starting the project. So I think this will also be a reason for us to be proud of the work done in these last years, and to be looking forward to have the real data, real Jpas data. So yeah, I think just to conclude, thank you very much to all of you who have been participating in this session. Thanks again to the organization of the SEA meeting, and for giving us the opportunity to be in touch during these 3 hours. And from my side, that's everything I want to say. I don't know if Pepe, also from IIA, wants to say something.
Well, thank you, Javier. I think it's far enough. You have said everything. Thank you to Silvia. It has been a fantastic meeting. I mean, the 15 minutes at the beginning were a bit exciting, let's say, but at the beginning of the meeting, and maybe our colleagues from from foreign institutions were a bit confused, but anyway, that was just few minutes, and the session has been extra. I mean, it has been very exciting. Yes. And yes, so thank you, Silvia. Thank you all the speakers and the SEA for giving the opportunity to Jpas to organize this virtual, very successful meeting, because I was counting over 120, in some cases, people connected, 110. So it's a great success. Thank you very much.
Thank you, Pepe. So actually, Alessandro was suggesting to take a group picture. We are less now, but you know, I'm not sure you all want to put your camera on. Let's see. Let's give it a try. We try for 1 minute if we can.
Oh, good.
Yes. Let's see. Okay.
Nice.
How do I have to do it? Okay. Sorry for the ones that, you know, had to leave already. Okay. Okay.
Nice to have the opportunity to see how so many loved faces. I miss you all.
Yeah, it's very nice seeing you all here. Next time, this will have to be hopefully with a beer and touching our hands, hopefully.
Mm.
Well, already it's nice to see our faces,
Yeah,
because
sure.
yeah. So, well, next year there will be the SEA in Tenerife. Hopefully, yeah, we really make it there. And with the first now Jpas results. All right, so whoever, I will take a few screenshots. So you don't all fit in one, so I will have to take a couple. Okay. If you also want to do it in the meantime, cheers. Hello. Smile. And, okay. One, and then let's try the other one. Sorry, yeah.
Carlinhos, you can put your hat off.
Okay. Smile all. 3, 2, 1. Okay. Great. Okay. I'll send it around to the collaboration and to the people that I see here. If you have any issue about posting these, because the session is being recorded, if you have any issue about it being posted anywhere, let me know, okay? Drop us an email, all right? Okay. Bye, everyone. And waiting for the beginning of Jpas.
Thank you very much.
Thank you very much.
Bye.
Bye.
Bye, 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 everyone.
Bye.
Bye.